consider. Right, so welcome back to lecture 3. And I hope you got now the chance to explore a little bit really, using the cluster in practice, using HPC-UGent in parallel. And throughout this lecture now, really use the cluster, right? We will have time after lecture 3 to come back to some results. We will discuss it together, clarify questions, but really change a bit the parameters, change the number of nodes, change from brain small to big brain and so on. And don't worry if you, let's say, here and there, just dive out of the lecture. Here and there, we'll be now doing this slowly because it's theory and in a way very important. However, we have in the end also a kind of data set we look at that we use tomorrow. So in a way, you can see this also as a preparation for tomorrow. But we left lecture 1 a little bit on a note of saying this is a little bit informal, and we will come back to some of the formalities now, not just for the sake of math, but also for the sake of understanding why learning is feasible, how learning works. So a little bit the tutorial on machine learning needs to cover that, because there are lots of pitfalls, and this is the best to understand it by moving a little bit into the theory, like overfitting. This is a very bad thing. When you hear this word, there should be alarm bells, and it will be mostly the problem in practice why your accuracy is very nice in sample, and we will discuss now what in sample really means, and doesn't reflect out of sample, so unseen data, things you can expect in the future. You basically create a model, you train it, you test it with your in sample, everything is very nice, you deploy it, and suddenly new data comes and your model is terrible. That is usually the effect that takes place when you have, let's say, overfitting. And we discuss a little bit around these problems. The slides will be online, so also no need to really, make notes. Let us just quickly review a little bit what we have learned from lecture 2 now. We go much more into practice. As I said, normally we would have continued in the university more from lecture 1 to lecture 3, thinking about, okay, now how we can formalize machine learning. Lecture 2 is more about data mining, clustering, unsupervised, digging in the data. And we have learned that there are interesting applications like the one here we have as a human brain with different cortical layers, basically using the cell density with Statistical to find different clusters and with this different cortical regions that have, by the way, different functions in the human brain. That's why we want to find out and map that to different actually patients. However, we have seen the trivial ones that we have here, k-means and k-median, which are very often used in practice, are not capable of the many interesting aspects that we have seen here. So those which are really, have interlinked clusters, which are not really convex. K-means and k-median basically have some problems. The difference is actually that just, this k-median picks one point out of the data set, while the k-means didn't do it. So it's just a small additions to the k-mean idea that the principle of the algorithm stays the same with this, just you have an in-sample property here and here not. However, DB-scan was much more effective, hence we have a parallel version for it for your usage, if you want, in your lab, for your scientific experience. In the break, I had a very nice chance already talking to some of you who have really interesting data to look at. Maybe not necessarily only with clustering, unsupervised, will be also an interesting topic next week when we have deep learning. Also there you can do unsupervised learning features in the data. So that is interesting. However, in our example here that we use, we have the laser scans, right? And we see a little bit, we have here again a smaller problem with Raymond. Now if you consider really the parallelization we discussed, the big cluster, of course this really makes sense if you have, let's say, a whole country to cluster, or clusters in certain regions of the country cluster, and there's lots of points to be taken into account. Then you come to the part where you need really a domain decomposition. That is what we discussed a little bit here, where you chunk now basically all your point clouds here for simplicity, just in 2D, and distribute it all over the different cores that you have, right? So by now, when you do the job script, you use already 12 cores, 24 cores, which are basically chopping down your data in different cells and then communicating a lot to get the clusters back to the different clusters that are in your data set. And we use the HPC machine here, but when you move perhaps somewhere also to another organization, You can always ask to where did you get HPC-UGent also there installed. It's open source for you available, and it works and scales usually quite well. So what we discuss now is a little bit back the supervised classification. We sort of started this in the first lecture. We're saying we have, an informal way of understanding what different types of flowers exist, if you remember. And we had a very simple approach to it with a kind of classification in two classes and no real mathematical formula and so on. And this will change a little bit now when we talk about the formalization. Still, I keep the mathematical really user-friendly, right? So if you go now to a book in machine learning and you will actually read theory of generalization, for instance, or statistical learning theory, it covers pages after pages of derivations. However, being applied more, it's not necessarily you need all of that. However, we have to talk here and there about some of the aspects, like why can we learn at all? And we see that there's some problems with it. And then the theory of generalization, which means we want to do something which behaves on unseen data very well. And this is, of course, a loaded question if you think about, again, the linear perceptron, which line to pick, and when we stop training. And these aspects will all, in a way, lead to the biggest problem we have in machine learning that I want to imprint in your brain, if you want. So if you go to the practice, you always have to take care of this word. And we will understand what overfitting means. Then in the second part of the lecture, which will be a little bit smaller, we will make a break here shortly, looking on how it is again, if everything goes well, and you can submit still and use different jobs. But then we prepare a little bit for tomorrow, already looking on some of the data sets we use, just so we have more time tomorrow, run the jobs directly in the morning, so that over time, the models get created. Also, the technicalities that we have tomorrow will be different than today. We will not just one job script, we have several job scripts, different ones, doing training, testing, cross-validation. So you will see the whole day will be a bit more complex using the cluster. Hence, it makes sense that we take some time today in basically here to think about what will be our applications tomorrow. Right, so starting again from our example where we left the lecture one. By now, everybody has so much basically clear. The perceptron is creating a line, we have a decision boundary, we have our data here formalized. A little bit now we're setting a labeled data problem, right? So we have always our sample data as an associated label. Let's look a little bit more as building blocks then in machine learning to formalize it in a structured fashion. So the first one we have really is the training examples, and this is something what we already know: historical records, ground truth data, and net cover classification, the brain data that we had. So this is something where there is data existing, and it was created according to some specific probability distribution. The good thing is we focus on supervised learning now, right? The last lecture was very much about unsupervised learning. Now we really go to the supervised learning approach of creating basically a modus operandi to establish a certain point, which is in the end the feasibility of learning. So in a sense, you know what we want to do already from a little bit thinking about what the perceptron was doing, right? We want to create something what we might call a function. And in some of the books it is called function approximation, some call it function development. What we first basically have to establish is there would be probably some function that explains our data, but it will remain unknown in machine learning. Because if you remember, one of the second ingredient was in machine learning, if you know the function already, if you know the mathematical formula, then you don't basically need necessarily machine learning. You just implement it, use it, and then it works well. So here we want to have some function approximated that we will never know. We call it the ideal function, right? The target function that has created our data in the first place, some natural process somewhere in nature, for instance, creating some of the beautiful sepal and petals that we will never know. And this is something that remains unknown, unfortunately, right, in machine learning. However, we try, of course, to get very close to it, this interesting fellow called F. Making this more of a structured recipe for you is basically this kind of layers. So these are elements we don't really need exactly to know. On the first layer, we have the unknown target function, f, basically which remains unknown. But then on the next layer, it's something that we must have. And this, if you remember, was definitively the data. Without data, we cannot learn. right? And we assume in machine learning that somehow this function has created these training examples. And this could be anything, right? Credit card approval records, movie rental records, ground truth data we have seen in the point cloud. Maybe someone has already there's more studies with it. Could be any data really. Then we have other aspects we will hear later with our skill set, and basically these are on the lower level and have to fill now with our machine learning competence. Things you learn here today and tomorrow, algorithms and hypothesis sets that we can use. So let's go ahead, because one of the first linear example you already know, we use it in the perceptron learning algorithm, right? So, and what I said earlier here, the exact formula, the target function, basically remains unknown because otherwise we don't use machine learning. But the real model you already used is the idea of just the line and adjusting it with the weights that we learn intuitively by going sample by sample through the data set. It is already a learning process. So creating this line and is basically the key question. Hence, how we formalize that a little bit, we would say we have now something we call a hypothesis set. So I put here big H for many, many models, right? Because now if your machine learning in practice means you don't have only perceptron, you have tree-based models, you have artificial neural networks, you have support vector machines, nowadays deep learning. You have perceptron learning algorithm is just one of the small H's here. And then if you think about inside this perceptron learning, you have different, basically, lines that you learn, right? And all of them are considered different hypotheses on your data. So all of this is basically contributing to the fact that we have lots of degrees of freedom to choose a model basically for the data out of our skill set. That things, of course, are learned, by studying artificial neural networks or SVMs like we do tomorrow together. And then I use all of these hypotheses, and finally, when I think I have a very good model, I pick a G out of it. Right? So you would basically pick G from one of these very much pages you look at, and then pick G and say that is your final hypothesis that you want to employ in the bank or the movie rental office, or actually want to publish a paper with, if you're in science. However, this creates a little bit of problem of M different hypotheses, the candidate function, right? Because here you have unlimited degrees of freedom. This is loaded, unfortunately, in machine learning theory, and this is a parameter or a problematic parameter we have to talk again and again now through the rest of this lecture. But we will concrete this a bit more now step by step. So when you do now a little bit of building blocks in mathematics, we have the first part. Now what we add here is our skill set. We say we learned a bit about perceptron today, not very fancy, but a start from machine learning. So tomorrow will be support vector machines, and then we pick one of the models. So we're approximating roughly this function very well. How we do this is still a big question mark. This is basically the theory of generalization, the things we talk now through. But these building blocks are very key essential in it. So the next, basically, final hypothesis, that is something what you already basically had in one of our examples here. If you remember, we had one that was very much working well, is all this weights set, and the bias as well, right? This one here. So this was the example where we said, now this is a model, we have learned the weights, and remember the x are constant. Right? And the y also, that is your data set that you get. So all what we learn are these fellows here, the w's and the threshold. By going iteratively through samples, and as we said, if you assume linear separability, then basically it will end up fine. And I should mention there's a tune to the perceptron learning algorithm. You can also measure your failure in the number of misclassified ones. So there's a tuning called pocket algorithm where you have the lowest error and you put the weights in your pocket and stop just after 1,000 iterations, right? Because this helps for non-linear separable data. But it's not so important because it's also a small trivial example and we want to go more sophisticated now tomorrow. So let's look a little bit on this. I think here is clear. We have now lots of options, lots of these lines, right? They are all in a way doing our job right. And all of these are H1 to up to HM. So we pick one, And the one we picked here in this particular example was just the first one, where the perceptual learning algorithm sees, by switching always back and forth, there is no misclassified point anymore. So I stop and I just report the weights. What will happen if it's non-linearly separable? Any idea what happens to the perceptual learning algorithm we discussed?
Won't converge.
Exactly, it will not converge. It will always continue. You cannot report anything, right? So this is, of course, then the problem. So you don't pick G because you can't, and then you're not sure what to do, and you're not ready and finished with the job. You maybe need a better model. So you switch in your hypothesis again, maybe from the perceptron to support vector machines we basically do tomorrow. Right, so this is the idea of this, but you also have seen that this goes together with some kind of learning algorithm, right? So we had the perceptron model. That was this fellow. But from this we didn't know anything how to get there. So we needed the algorithm, which was a perceptron learning algorithm, adding or subtracting a vector. These are two different things, which now should be more and more when we formalize this in your brain and in your mindset when you think about that is a skill I have. So here we talk, for instance, solution tools. That is where you come to a problem, to a customer. You say, okay, what data do you have? And then you think about, okay, that's the data you have. I want to go there. Let me look at the data, and then you think like, okay, perceptron, linearly separable data, perceptual learning algorithm goes to that. Tomorrow we will learn, we can use support vector machines. The learning algorithm will be quadratic programming and sequential minima optimization. It's not obvious to you, you see how that materializes tomorrow. Neural networks, right, is a model, not a learning algorithm. The learning is done through back propagation of errors. So they're all the models that you have here, and even deep learning has a kind of tuned version of back propagation because it's still a network. So you would have always these other solution tools, and you keep them separate. They work together, but in creating a model, you need to keep that for a while separate. And the reason is that for one of the models, there could be different tuned versions of the learning algorithm, for instance. Anyway, let's put that in our diagram to have a better view how all the different pieces in machine learning belong to each other. So here now we have our skill set saying, this is all the artificial neural networks as we have these trees, decision trees, a very big topic we can't cover, unfortunately, very interesting indeed, and learning algorithm that goes with it. And then when I do all of this, I pick one G and report my function. Now all this looks so easy. Our linear example has kind of proven it now. I guess you get the whole story. We never know that, but still we get something like this, real data, where we can find a solution. Right? So very nice, and the perceptual learning algorithm was just doing this. This is simple linear function, very easy in a way if you think about what is possible in mathematics. So this is interesting, and so this works very nicely. And where is the problem now? When we think about now real data, there should be a bit more the exercise now in thinking. Parts of it we already discussed with the lines, but what could be potential problems when you go further? Perhaps when you think about the perceptron learning model, one we just discussed, it will not converge, right? So the exercise is now thinking about this. So what could be other problems when you think about this model, perceptron learning algorithm, when you approach now data sets? Think about how the learner was. Okay, someone opted out for that. Okay, no idea?
Can you repeat the question?
Yeah, sure. So what do you think would be more challenges when you go now to the data and analyzing it with the perceptron learning model? So what could be problems you face when you think about what you learned, decision boundaries, or perhaps aspects of the data? Yeah, there's a statement.
Maybe the activation function, which is not a sign function.
Very good.
Simple.
Yes, exactly. You have here the kind of linear approach to all of this and a very simple model. So maybe we want to have something which is perhaps also non-linear as decision boundary. Right? So if you think about now data needs to be also linear separable, is everything aligned? No, right? What about you have kind of cluster right in the middle? is one class, and surrounded will be another class. Right? So we have to think like more what would be potential problems here. Right, in the light that we already have some advanced time by the advanced break in the beginning, let's go a bit quicker through this exercise. There are lots of possible ways how we basically can think of how your data was created. And this refers to a probability distribution on the data in theory, which we also don't really know, but we assume. Right? And it's the next interesting building block in machine learning, which actually puts us aside from Bayesian and also from some of the statistical approaches that you have in understanding data, because they assume some certain probability distributions. We assume also that the data that we created was based on some of the probability distribution we have, and from this it could be linear, non-linear dependencies in the data. So all of this, where perhaps also the perceptrons will just fail because we can assume the data sets that will come in the future will be not behaving by just being differentiated by a line, of course. And then, of course, if you think also what happens, that was another part of the exercise, if you don't have a two-class problem. How do you do that with a line? Hard, right? So you have to think about, probably you need multiple lines, and actually that is the advancement that the artificial neural networks do on the perceptron. However, the formalization here a little bit around, what model you in a sense need from your skill set is a little bit partly derived by that. So what is the probability distribution behind that? And if you now think about that, we're facing data that could be anything really, we kind of are in trouble in machine learning. Because the question is, can you learn at all from something we don't know even? But we do some assumptions, and this helps us a little bit of saying, we don't look at random data, right, which is a key statement now here in the theory. We assume that the data items we go through in machine learning, our samples here, are coming from the same probability distribution. Which one is independent of our thinking? Could be anything, heavy tail or whatever probability distribution you have, or normal distribution. Basically, we just assume that we don't pick arbitrary data. So in a sense, it means when I have now movie rental data, I don't necessarily combine it with a Christmas market in Cologne attendee, counts, or something which is completely a different random cycle, completely random, has nothing to do with the data, was not created from the same probability distribution. This will be very difficult, right? So this is something what is the next building block based on this. And we see with this a little bit, we're talking about probability. And this is a very important statement we actually create now, which is unfortunately a little bit theoretically, but it is kind of the idea of why we can say something at all out of sample. And these are the two notions I would like to establish here a little bit. When you now think about what you have in a typical situation, like you're picking your marbles, for instance, in different colors. Right, you would say those that we have picked, the data set that we already have for our machine learning, this is always our in-sample. Right? This is a notion that should be in your mind. The data set that you have to work on in machine learning is in-sample. However, what you are interested in is making a machine learning system that works very well here out of sample. But out of sample is unfortunately something which we will never know. Right? It will be unknown. However, if you know a little bit about statistics, there's a nice point that we can have some, let's say, probability. If they say they're on the same probability distribution, that's why we put this probability distribution umbrella around it. We can use a bit statistical knowledge of saying the likelihood that basically the in-sample kind of coloring here will follow what is out of sample. Right? So this is the statement that you have approximately correct, and just measure here this E that you have here is basically the error that you have in sample and out of sample. That is basically the quantity that you're interested in knowing. So this is something we actually can measure in a sense because we have the grip on in sample, but we can never make a statement of the error basically out of sample for a specific hypothesis. So this is a bit problematic, but helping with this kind of statistical knowledge of saying it will follow suit, right? This is basically the key breakthrough then of thinking why we can say something at all about data that we will never know. And initial practice shows that this is possible, but you should consider this then as basically learning is feasible, but only in a probabilistic sense. Right? So only if the data is derived from the same probability distribution, we can make the statistical assumption that the next data items will be not completely random, but follow suit. And with this, we basically can come to the notion that the out-of-sample performance here that we will get from our specific H, from the hypothesis we are looking at in the moment while doing our machinery, will basically tracking that the in-sample. And this is kind of the statistical learning theory. And if you go to books, it will have pages and pages. I really make it here short. In the university, we have around 3-4 lectures just basically around these topics. And the next one, which basically says like an important rule that you have in machine learning, which is a packed statement. It's probably approximately correct. It has something to do a little bit with this bad factor M, if you remember. We said like every line will do, right? So if I can say every line almost will do, it's an infinite number of lines. So how we can choose or how we can pick something from infinity is the next big problem, right? So you have lots of options, and this is a bit a problem. However, what we want to achieve when you think you pick the final G, right? The one hypothesis you want to use in practice. You have to handle on this, which is called the Höfting's inequality shown here, right? So we assume that the in-sample error that we get on this deviates basically by the out-of-sample performance of that, because they follow suit, just by a small tolerance. And we use here the absolute value and make a bigger sign, right? Normally we would say that should be small if it follows suit. Here we say it's bigger, which means basically this is an event we don't want really to happen, right? This means basically if this is really much bigger than epsilon our tolerance, it's something that we don't want. They want to be close to that together. We want to make a statement on the error out of sample. However, this statement helps to create, interestingly enough, something out of the mathematical toolbox of saying the worst thing that can happen, which is, this bad event here in the sense that they are not following suit, is a combination of all possibilities that can go wrong or are bad. And with this, you are in a mathematical toolbox called union bound, which is, again, the probability that, all the bad events, and, move through all our hypotheses. And we said we have infinite ones. M, factor M is infinity. We go through all of them and add them up. We basically create something like this kind of statement that we can then make more easier, and let's say after the chain of derivation and mass, you will see we add here and here kind of several factors, but this is the kind of final result after going to 30 pages of mathematical derivation. So what it means, right? So when you go a little bit firstly on this red factor M, this is really bad for us firstly, because this means it's firstly not anymore Höfting's inequality, because this just relates to one hypothesis, just to one experiment, and we have to extend this here to the M infinity ones. But we will take care of this factor later, right? There's a smart way of taking care of this. Much more important for us is, if you remember what this means, so this was a bad event, right? Where we said this is, subtracted at the absolute value more than our specified tolerance. This probability will be smaller than this. And here's good news. Depending on our n, which is the number of samples we have in our data set, we can say that the probability of this bad event happening will be small. Right? You see that? It's in the exponent and minus exponent, so this will basically getting smaller and smaller. And with this, we can say the probability will be hopefully less than 1 or something. However, there is a stupid factor m you have to think about now. Right? So infinity is bad in this equation, so we have to take care of this later. But still, we see that the probability of bad events, maybe depending on n here, the number of samples we have in the data set, will be, diminishing. In other words, learning is now again feasible if we have lots of samples. If you now have a factor of n with 5 samples in machine learning, and you want to do something, you can see that this probability will not hold. Right? If you just learn from 5 samples, you cannot make an estimate out of sample. You lose the bound here. right? We have 2 less samples to train from. The probability will be, the bound will be 2 less. Ignoring factor n for a while, admittedly, but there's a cure for it later on. Just, think about this when you this is a kind of, let's say, predecessor to something we call then the Wipnick-Shelton-Menkes dimension and so on, which is much more theory, which we don't go today because we want to have a practical applied session. However, let's keep in mind that factor n, we will come back to this again and again. So this is basically already that what I was saying earlier. So the important thing to take away is really this PAC statement. So whole books in machine learning have a chapter normally of saying PAC learning. So what is PAC learning? That is something that we should clarify. It is basically that you have the probability here, right, as we discussed, depending on your number of samples. That's now the link to the data, the real data that you have, right? And in a sense, if you say the more samples, the better, you can have probability this, and with this, your kind of small factor in between of saying a limit of tolerance should be there, right? If your data is not linearly separable, and just a couple of outliers are there, you would give a little bit of tolerance and say the outliers don't matter. This means approximately this statement is correct, and this means probably approximately correct is a statement of learning. Right? And this is a PAC statement, which is a key part of the statistical learning theory, basically describing again that learning is feasible, but only in a probabilistic sense. You cannot guarantee 100% for sure. For instance, when you go to the bank, I can not predict the stock market 100% correct. Also, when I see, when I talked to you earlier about overfitting and so on, 99% accuracy, that's usually something where your alarm bells go on in machine learning, right? Usually you don't have basically this exact aspects. However, you see in terms of big data, n would be basically good to have lots of samples. In a way, then also some have asked me when is the right number to learn from the samples in the break, right? They asked me what would be the number. It's hard to judge because it also depends how strict you are, how approximately correct you want to be, right? So you have, let's say, different parameters on that. Still leaving out n because we take care of it later. So this is kind of the summary of the statistical learning theory, why learning is feasible in a probabilistic sense. If you want to learn and actually look at the mathematical derivations, of course, you can look at here a theory of the learnable, and there are lots of mathematical derivations to look through. However, this is at the end result. Not completely the end, if you remember, we have still this factor n we have to think about. But there's a practical solution to this problem. Right, so looking at this, we add this now to our probability distribution and say the data and the training examples are not coming out of the blue. I have historical records in a bank that say something about the task at the bank, right, and so forth. So that's something where you have some, link still to the reality and what you assume. Another visual expression is perhaps this one, when you think about now, you want to learn from these kind of things, the probability that the next points, in our example here with the points, lies somewhere close to this is very high, right? And this is what basically just the probability distribution over the training example says. The assumptions we have to do in order so that this assumption actually holds true, right? So this is something very important in machine learning theory and holds basically true for all the models. Now from the exercise point of view, I think we skipped that a little bit to be more in time because we were really lost in the beginning a little bit of time. It's more a theoretical exercise at that point of time. Perhaps any questions before I go further? Now it's a little bit theoretical, I know, sorry, but it's something that you really have to get in your skill set. Okay, going once. No questions? Twice? Okay, if not the case, let's go on a little bit. Because what we now need to do is how we get better. Right? So that is the key question to ask. And the key question is answered with the error measure. And this is of course something which is now very flexible, depending on your application domain problem. One example here, which is a very, let's say, usual measure is a point-wise error measure. If you remember, we have our hypothesis that we just pick from our skill set. We use a neural network, we use a perceptron, SEM, we use it on our training set data, and then compare it to the f of x. F of x is nothing else as our label, right? So we know from this already the results, and compare it in point-wise over all our data set, and then can basically improve ourselves by always measuring if the error gets down or up and so forth. However, this is one thing. The problem is in learning still, this interesting fellow. So this is something what we have to discuss a little bit from the practicalities. Again, it's a little bit more elaborate in math, but think about it more from a practical perspective. You're watching a movie now, and you're watching the movie, let's say, for instance, in a year, right? And you have the same person as X, right? You as person don't change. You have still, the same address, you're still the same credit card number paying for. So all of this doesn't change, but you give a different rating. You don't like the movie, let's say, anymore, or something like this, which means for a function, the same X, you as a person goes in, and different Y's come out. Any mathematician here? Normally they would scream now and would say, is that possible? This is not possible, right? It's not a function anymore. You cannot have different, the same x with different y's out of the function. That's not possible. Hence we put a target distribution over it of saying all of these are basically having some part of noise. Hence we call it noisy target. And this is something which means like there's always something we can't capture in the model. Either we don't have it really as data there, or our model complexity is just too little, right? Assuming, for instance, there's a high nonlinear dependency in the data, something very tough as a pattern, and we want to catch it with a perceptron learning algorithm, right? You see it doesn't fit, right? The model complexity is also considers the data as noise. Basically, it's something we cannot reach for. And these are different types of noise that we will look at too. But take away the message that in a way machine learning stops here, and this differentiates us again from other fields that do just function approximation by assuming a certain kind of probability and so on. So this is different. Let's put it in our diagram to be correct. Firstly, when we do a learning algorithm, in order to get to the G that picks an F, we put the error measure in. That is something we speak application specific, and of course can be also intensified. So if you have very sensitive systems, you should make sure that the error measure is very strict, and so improving the learning algorithm over time to get hopefully to this one fellow G with lots of improvements in the error measure going less and less. So this is the unknown target distribution that we load there in the beginning as well. Hence, one example of this we have already seen, the error that we had always counted here, right? This is also our error measure. We look at, is it really the sign of the function equal? If not, adding or subtracting a vector, doing this again and again. The error measure we will see over all the samples will at some point in time be zero error. Why zero error? Because we have linear separability, right? And there would be all of them rightly, correctly classified, otherwise the PLA will not converge. Okay, this is basically then the error measure that you use here in this part. So mathematical notations a little bit, when you think now what we have in terms of different processes, is this, when you do training, we have basically to cope with this M factor. We go through all the methods, if you remember, right, which are infinity, which are very bad for us. So we still have a few later on. However, when you think about testing, that is very clear for us. And also there, of course, you have the N factor now, which is interesting. So also in your test set that you should have, you need a representative number of samples. Otherwise, this testing and so on will also not fly in the data. The evaluation of the model will be just not following suit the same way as we would have in training. Hence, both are related heavily, the training and testing, to the amount of data you have available. So then this is the training examples, and we use them for training and testing, so you have to cut them. That is something we already had in the lecture 1 at the end. And just for you as a takeaway message, there are different phases really in learning, right? And this is an important part that we will explore tomorrow much more in depth. That's why we have different job scripts for training and testing tomorrow, for instance. Right? So today we used just one job script, a little bit of data mining, there was not really training, testing, and so on. So this was just a little bit of clustering and supervised. Now we go much more sophisticated, having training and testing as different processes. So why is that going to be useful? Of having training and testing?
To select a good model.
Okay, yes, to select a good model, yeah, right. Another statement maybe? A very shy audience here. Yeah, please go ahead.
Check how well your trained model regularizes to unseen data.
Very good, yes. Out-of-sample performance again. That's where we're interested in, right? That's why we need not only training, we need testing. If you remember, we throw it in the corner, we don't touch it. Then we work on our models to training, and at the end of the process, we're really sure we use the testing again and basically use it then to report some accuracy or some error rate, which was another answer, for instance. We need to have concrete numbers. And that's why, compared maybe to many big data analytics topics, machine learning is a very nice topic because you have concrete values, concrete accuracy values you can mostly report with evaluation and testing. That's one of the answers as well. Right? When you think about, you go to a decision maker, he wants concrete numbers. You cannot say, well, I improve your system by some degree, and I get the check. Normally a CEO would say, turn around, come back when you have something I can really, grip in my hands. When you go back and say, I improved the movie rented by just a couple of percent, like 3%, 4%, 5%, this means an order of revenue for my customers, multiplied by the millions of movies that are there. So then you are into the game. You need concrete substance numbers. In order to report them, you need the testing and the evaluation that is behind that. Tomorrow we will go even one step further into validation, which is another set, which I keep here now for the sake of complexity, not inside this one. So again, you have to go a little bit more into some of the limits and of generalization, which was a very good answer that we had in the beginning. Of course, the generalization matters. Now, when we have said a bit about it, like we have infinite number of models, and the probability is smaller than equals probability of infinity, that is not really helpful. So we have to think about this more and more, and actually also how we learn better. And these are kind of two ingredients in the reasoning. So firstly, we have established this, right? Where we said the out-of-sample performance is likely to follow the in-sample performance of our model. That is very nice because we can do everything we want in the in-sample now. And what we do in the in-sample, the out-of-sample that we will never know, some data in the future will probably follow suit. That means we have a handle on it more, basically, right? Which in other words means, of course, what we want to achieve is this, right? We approximate almost zero with this, means we want to have almost zero errors out of sample, which means we work on in-sample to get this lower and knock it down if you want. Right? So in-sample performance, if this goes in the error rate towards zero, we expect that the out-of-sample error rate goes also to zero. And this is now the problematic point where overfitting alarm bells start, because this is not true. It goes up again, and we will see why. And of course, this is a problematic quantity, but E out, but we know where we have the handle on E in. And this gives us, let's say, two core building blocks to work on. The first one is we cannot use this one, the out of G, but we know through this interesting deviation that we created there that they are actually follow suit, which is the first core building block we discussed already. And here's our practical core building blocks. Now that all the algorithms come into place, right? That's what we do formally. Nothing else than say the in-sample performance error. And this why is many of the machine learning algorithms are optimization algorithms. Optimization against the minimum to actually get the almost zero error or towards zero error in the in-sample, and then we basically, with this kind of aspect that we have established in the first core building block, can say something out of sample as well. And this is now nice, so we have, let's say, this kind of thing automatically following, and this is what we can steer. Now here's our work, which is a very practical work, right? Systematic with all our hypotheses to knock down this E error in sample. So still we have the infinite spaces problem, if you remember, right? So this is something where now we have so many models, how it is likely to work out in practice. And here maybe there would be another question coming soon. Anyone has an idea, if you perhaps think about retouching always the same data, if you think about the line, different hypotheses, and if you think about the union bound we established was always bad events that had nothing to do with each other, right? But if you think about the lines, maybe just a little bit switched. Okay, no. They touch the same data, and the space that you basically have for classification also tends here and there to be very overlapping. Right? Even if these are totally different models, the line here, the line there, very close to each other, the space that they cover are extremely overlapping. So in a way, we kind of should model in our brain, it's not necessarily infinity we're talking about. It's still lots of lines, but maybe our interest relies not only on the decision line boundary, but more about the space. Right? Because when the new points will come, or the new data will come, they will land in the space. So this is something where we now target this bad factor that we have established with the union bound of establishing the worst that can happen to my data is it will never follow suit. But that is actually not really true in practice. So, and they have lots of challenges. I can go in more details. There's lots of parameters. Neural networks, for instance, have different number of neurons, different layers. Support vector machines tomorrow, we'll see we have kernel parameters. We have then outside the kernel parameters cost that we associate with the model to see that some of the errors are low. Things you don't know yet, we'll come to this tomorrow. But you take a message already, I think that this is quite tough to choose from. So now, how we get over this now? This was the question to you. And this was the solution now that we basically offer from the theory again, which is nice, because this solves now this factor n. And this is alluding to interesting pictures you see here, because when you think about the line, that is one hypothesis, right? Which could be one out of these infinite ones, and another one about infinity. All we are interested in, basically, would be the change, which is the delta here, basically the E out of sample that we not cover in the space anymore. Here is basically no point, which means, now think about when we create our model and we're changing the line, the point will not change in colors, or no point will change colors. So if I do now 1,000 lines or 1,000,000 lines where there's no point changing colors, there's nothing happening to my data, do I care about that? Why should I? Right? So even if there are 1,000,001, let them be. I have my data, that's where I measure my test set later, that's where I measure my model against. I don't care. The only thing I'm interested in is perhaps this one, right? When I change my line to some certain degree where there's a color change, right? And of course, this is a simplified version of the theory. It's also for multidimensional valid, but here for the 2D best understood. We are only interested in those events where this actually happens. And this gives us now an interesting link, right? So we think about infinity of models, but a very precise number of samples we have in sample for us. And now we think about, oh, okay, there is the dependency of saying this factor m we can maybe exchange with something related to the number of samples I have and their colors. And here in the kind of simple example, you can just simply calculate it, how many possibilities there are. And hence you come to the solution of finding a better bound to your probability. I like this visual expression very much. It's in the book from Caltech, Professor Abu Yazef, and then he basically describes it very nicely in this kind of way, where you have Höfting inequality, the one we started with, without the factor of m, if you remember, right? This would be nice, but cannot be used in learning. This is just verification, or just testing. We have already our hypothesis done, and then we can derive from there where basically our data is. Then we had this M hypothesis, where we said the union bound. Okay, all worst cases, the models have nothing to do with each other, infinite number of kind of lines, but we know from our example that's not the case, right? We can always go back and say, let them be millions of models, I don't care. The only thing I care is about when my model changes my data. That's the only grab I have, the data. And hence, in a way, and this was really then the breakthrough that Chernonekis was doing, is basically in the theory that you can exchange this factor towards a big Chernonekis dimension and the complexity of the data and get this to more overlaps. They talk about a growth function then in the theory, where you see it's largely depending on your hypothesis, depending on n, on your number of data items. So it's not infinity anymore. It has a relationship just about the complexity of the hypothesis and the number of points. In a way, that is a quick summary of two extensive mathematical lectures, right? So of course this is normally much more elaborate, and there are of course proofs, mathematical proofs, which are out there, which you can look at. They're not actually that extremely difficult, but absolutely also not trivial, I have to say. But here it's basically kind of a mini hypothesis in the sense that largely of them are overlapping and that you can always go back to your factor n. With this, we call it then also away from the Höfling anyway, because of the infinity m, not anymore the Höfling inequality, and the breakthrough in learning is really the Chernonekis inequality that you have here. The factor m infinity is now projected basically back on the points that you have. With this, we have a quantity we have and can measure, and with this, we have the characterization of generalization. Again, think about factor n is loaded. Again, it shows the tight dependency to the number of samples you have. N is the number of samples. So if you have very little samples, you know, your growth function will be also not really working well, and you have a very probability of being small and will basically have lots of problems in learning. So you need a lot of samples to work basically and to generalize well out of sample. Right, so this is nice because now we established we cannot learn, firstly, and now we remove this problem of cannot learn infinity with some substance that we have something we can measure in the data, the factor n. So what's the problem then? The problem relies, again, in certain aspects that we call overfitting and the problem with the model complexity. So in a way, you would think now we can just train everything long enough, and then basically it will always be at some point in time zero error, and then we report that. But unfortunately, that's not learning. And some of you know that. When you think about now you have an exam, and you look at your test exam, right? And you kind of learn from your test exam again and again and again. And do this intuitively, your error in sample on this test exam goes down. Right? You will be more or less memorizing everything, what you have done there. Right? Leaving alone the university lectures, because professors tend to tell a lot of things, I concentrate on the test exam. Error goes down. Now comes my real exam. And chances are, at the beginning of the task, you see, oh wow, lots of them are very similar, like, oh, but there are lots of them that are not actually like the test exam. So your error out of sample goes up. That's a nice analogy. And it's a little bit also related with the model complexity that you see here. So the more the model complexity goes up, the overfitting and your out-of-sample problem will actually be starting as well. So this is an interesting factor which is related to the Chernonekis dimension, a topic which requires a complete university lecture in a sense. Think about it a little bit on a handle of the model complexity. Right? And this is something where I mean, when you have a very simple data set like the ERIS data set we had, linearly separable, 50 samples on both classes. If I use this one now with a sophisticated SVM, that would be already very tough. We have a lot of high complexity and very little data to model from. If we train a neural net on such a simple problem, this would be by large, let's say, not really fitting to the model in terms of complexity of the data. So you go up in the model complexity and then suddenly find yourself beyond let's say, this interesting point where the model complexity, in a sense, should match basically the part. Otherwise, in order to get this training error down, because otherwise you will be going up out of sample, right? So here again, our learning algorithm will always do that, and will probably succeed even in that. But that doesn't help us, unfortunately, because this is what we're interested in, the out-of-sample performance. Now there's some cures for that, by taking some, second samples and so on. We then come to the generalization bound, but this takes too much time. We want to also have some time for the practicals. But in a sense, that's already the key achievement that Watnik-Chervonenkis, who was really a key figure in machine learning, has done basically in this part. In order to motivate elements we do tomorrow with overfitting and so on, tackle this. There are basically two cures for overfitting. This is basically regularization and validation. Right? So this is something we will talk about tomorrow when we have SVMs, so that you always have a practical tool to really understand the learning. Because otherwise we will go more and more theory, and this course will be a little bit practical. However, I brought you a video which is really the best explanation before I draw here on the board and do some interesting figures. This video is really a nice one to show you perhaps the most difficult problem we have in machine learning.
An example where the decision boundary was really, really complicated. So we have a situation like this. We call this overfitting. And it's a common phenomenon in machine learning that you have to be always aware of every time you do machine learning. To give you an example, if you look at the data over here, that seems to be linearly separable, a decision surface between red and blue that looks like this correctly classifies the red data, but looks erratic at many other places. That happens when you take your data to Riedel. And when your machine learning algorithm produces something as complex as this, as opposed to something as simple as this, you are overfitting. So in machine learning, we really want to avoid overfitting.
One of the ways that you can control overfitting is through the parameter of your algorithm. So in an SVM, we have several parameters we've talked about. C, gamma, and the kernel come to mind. So which of these do you think affect the overfitting potential of an SVM? Click as many as you think might be correct.
So we just saw an example where the decision boundary was.
Right. So this is something you cannot really answer today. We will do that tomorrow. But I know now what I guess you know now what the kind of overfitting problem is from one perspective. And this perspective is this wiggly curve, right? Polynomial to the whatever degree that is really forming a pseudo data. Think again your test exam, right? You take every task here in your test exam literally. You memorize it, you know exactly the answer, and then suddenly you face new data, a new task, which is very close to this one, but is here. And because you don't study the other material from the lecture series, you have no idea, because you memorized just what in the test exam. You didn't learn the material of the lecture, right? You didn't look on the principle, you just looked on this data too long to just have, it memorized. And this is a key problem in kind of machine learning from one perspective. And the second one I want to allude to is, and we talk about this tomorrow again, is the complexity of the model. I said in the beginning this morning there's a concept called Occam's razor, which says simple model always better, right? This is here, for instance, true, where you see this is a polynomial whatever, and in the very wiggly curve decision boundary, actually just a linear model would help. Very less computing, very much, not a problem with overfitting. We could see that probably the next items are very much closely to the probabilities we would roughly assume to those red or this kind of circles. Right? But this is a key thing. I really want you to know code every time you stand up in the morning when you go to machine learning. What would be questions related to that? Any questions of you related to overfitting and so on? Okay, if that's not the case. When you think about, we have not too long. Okay, no, there was a question.
Practically, what do you do to avoid overfitting? practically?
Sure, right. So basically, as I said, we have a tool set of two things, which is regularization and validation. So what do they do? We do that tomorrow, step by step, but I give you a short glimpse before. So a regularizer is mostly inside the model of making it simpler, of not taking the model too hard. In other words, you could also say allowing some errors. Right? So when I think now, perhaps in this example, where you think there would be a red one here, one of them, or two, and you would have now the PLA of saying, it's not linearly resemblable, but in a way, still the line would be much better than having a very wiggly curve. So what the regularizer will do with the kind of C parameter that we have seen in the video, this cost, will say a little bit of errors is allowed, or it will penalize the model, right? It will make it automatically to a smaller model. And I have there some examples where, for instance, decrease the polynomial to some degree, of just making it much more smoother. This is the first way a regularizer really works, right? You make this, in a way, the model simpler by not following every different outlier. So secondly, what you have is validation. Validation means you have a different data set, and this is something which we have at the end tomorrow, so you have to get a little bit broader in this. You have to pick parameters for these models. And now, to prevent overfitting, you have to think about which of the models you take now, right? And the validation will then pick specifically in a systematic way your model parameters. That means you do small training studies on validation data to see and estimate the out-of-sample performance. With this, not to fully train, just to basically estimate. It will be another handle we talk about tomorrow, and then basically get the right parameters. Hence, you would, for instance, see which polynomial to which degree is reflecting the data better. And this is a really practical topic where we will talk about where also HPC has the most input or most benefit in machine learning, where you can have them on the training set with cross-validation, basically lots of things done in parallel of estimating the out-of-sample performance. This will be a topic validation, very practical, because we have in a systematic way in a grid search finding the right parameters to have the model complexity right for our problem. Secondly, regularization is mostly embedded in the algorithms, like we see tomorrow in the machine learning, and not in the maximum margin classifier, but it will come then with this SVC and in the support vector machines, that really there we have a handle on the cost, allowing some error to happen. And this is the key idea of regularizing. When you have artificial neural networks, for instance, another idea of a model, it will learn the weights between the different neurons. I'll put it a bit abstract here, but it will learn the weights, making significance about your inputs. But here and there we have weight drops. So you just remove one complete weight, arbitrarily, randomly. Or what you can do is weight decay. You penalize the weights over time. And this again helps to actually not creating these wiggly curves, but see a much more rougher idea to the problem, much more rougher approach, which the regularizer is doing. That is kind of the literal saying about this. Tomorrow we will have, of course, some slides where we go through and having some examples that we can follow. Right? These are the two cures basically we can do to prevent overfitting. Good question. Any other question related to overfitting? Okay, everybody knows the danger of it, I hope, right? So we expected to have out of sample the future points right. If we have such a wiggly curve, we have no chance of getting future points right. Oh, there's a question, yes.
What about when we don't have not so much data, how to overcome overfitting in those cases?
Right, it's a very good question, and usually one way you simply often fall into. So there's different cures for it. Nothing works perfectly. I mean, to a certain perspective, here and now and then, if you have really, really less data, you have to think about this fellow again, if learning is possible at all. Right? If you have too little data, you basically have to say to the guy that comes to you with data and say, sorry, I cannot really do a reliable estimate. However, there are certain tricks, for instance, when you think about, as a concrete example, images, right? Google does, for instance, as you know, cat, dog, this kind of image classification. You have data augmentation techniques, where, for instance, you just change a little bit the pixel values or grayscale values, and you have a complete, in a sense, new picture to learn from. So you duplicate, so to speak, your data automatically. So this goes all into this direction to prevent overfitting, just to create more data. Because if you have too less data, chances are you have no chance of learning at all. Those basically, the established public channeling inequality will not hold. So, but there are techniques to create more data, if you want, from data augmentation in many ways. Good question. Please feel free to ask anything. I hope in between you check also the HPC scans. Perhaps now is 5 minutes, just check your HPC scan runs. Submit a few now, we break for 5 minutes, just a short break so that you can submit other HPC scans, because we want to discuss it towards the end, what you got. Maybe increase the notes, or if you have not done so, switch to the Bremen big data set, right?
Yeah, maybe you can show the job script for each 5 to see how.
Ready. So for those of you who are interested in the break to explore some other parts, let's go a little bit into one idea that we can do here in terms of the transformation from the HDF. If you remember, we had some problems with the right Python version and so on. And actually Kenneth worked in the break already against this and had a nice solution for that. Let's look at this. We have a script that we can actually look at. Which is nothing else than a job script. Let's put it here. Where, on the cluster there will be the right versions, everything automatically done. So in a sense, instead of just doing it on your command line, right, what you can do in terms of transforming your data now from HDF to this interesting point cloud data is just using the cluster again for it. And we put here the right module to load, or the right Python version. And of course here, it's a little bit depending now what is your job outcome, right, that you want to use. Remember, you don't want to necessarily use the one that is now in this directory for clustering and Bremen, because it's unclustered. So now you either copy it basically manually, or you basically go to the location where your file is, that was basically coming out of your first job, and look at this. This is of course then important that you have to specify. And then you basically here automatically get the script executed with this particular file, and the outcome of it will be then similar like the Bremen clustered point cloud file that you then can use with the slide content on the point cloud viewer. So what I will do, firstly the script is there for you to use a QSub again to do the converting, but secondly I will do an updated version of my slides including this job script, so that you have, after this kind of an updated slide set, including this as well, so that you have here the chance of really using your output, because you would probably be interested in looking at your Bremen clusterings, when you change epsilons and change the minimum number of points and so forth. Okay, but use the time, please, really submit to the cluster. I hope you're still not so full yet, there's still some capacity left. So play around, right? We have a reservation, it's nice to use it. If you go to practice back to production, that would be not the case, right? You basically have to get grants to get core hours on machines. Here and there, as a student, it would be probably easier, so the professor is doing it for you. But in Jülich, our systems are, for instance, always 99.9 full. So you basically need to always have grants to use the system. So it's very nice to hear the possibility using your your different models, try out the different parameters, and so forth. Yeah, 5 minute break, I would say. All right, okay, so I see lots of people using half-fidelity scan, changing parameters and having interesting runs to cluster, very good. Also think about this, you can do that this evening if you want, basically until 7 there is a reservation active, but even after that you probably get here and there scheduled, so don't worry. Just the kind of reservation will end at 7 and starts new tomorrow morning, and we then use support vector machines. Anyway, the codes and everything we discussed, including the files that we have seen here for transforming the point cloud to the viewer file and so on, will be available for you. I would like to, I know all of you have been now going with me a little bit through a short walkthrough through the theory, and I'm a little bit tired. So just a little bit of preparation for tomorrow morning so that we can start very fresh tomorrow. I would like to have some slides around the remote sensing application as a sneak preview. What will we have tomorrow? Tomorrow will be a bit more applied as we have already no knowledge of job scripts, as we know how it works with a cluster. So you can directly more into practical settings. The theory is over, we have basically learned about that. Hence, here and there we make some links back to the theory with regularization and validation to cure overfitting, as we said, right, from a practical perspective. And we see the step-by-step in SVMs how it turns out, until we are actually at the end then doing cross-validation. This will be very interesting for us, because in many ways and one, it has actually the most benefit in parallelization that we explore. Right here now and then, I think some of you have already experienced speed up and HPC scan now, of increasing your nodes or your number of cores really working on the problem. In cross-validation, you can also go really significantly parallel and have interesting aspects. So what is the application domain we will have a look on tomorrow? And we'll start by this, just looking on the data. For some certain aspects, I will come also tomorrow when we think about linear separable parts. We left this a little bit unclear, and this will be tomorrow clarified basically in the next lectures that we have. But we basically have here an application field which is remote sensing, so you have satellite data actually measuring the spectral channels from the Earth, so you have up to 200 dimensions basically of different wavelengths of light. That is a little bit looking like a cube. So if you think about now that the satellite is taking images from the Earth's surface, you can really consider this as, of course, a two-dimensional thing. But having, the spectral information that we have also, making it a hyperspectral or multispectral data set, we have these different wavelengths of light that you have for one basically pixel that you measure with the satellites. You basically look into the Earth and can from this derive perhaps which material it is, and aspects like this. So it's a very interesting field to study called remote sensing, of really having very interesting data sets that we will look on tomorrow. And here's one example which is a little bit smaller, just to make the linkages now to many of the topics that will come tomorrow and that we had today. So today we had a very interesting example classification with two classes, right? That was a very basic assumption. Now when you look now on the remote sensing, here's the city of Rome from a satellite. So here you have the different classes. It's not anymore two classes, you have basically 9 classes. Also, the number of samples that you see is not anymore 50, like in the IRIS dataset. We have for each of the classes quite some training and test samples. Right? And here you see also the very important aspect, as I told you at the beginning. When we get the dataset, we cut it into training and test set. Right? Very important. Then you take this test set, throw it in the corner. You don't care about that anymore. At least until we trained the model, we understood a bit better what we're doing. We have a model that we want to then test against out-of-sample performance. So how that will work is basically a little bit like explained in all of this kind of part that you hear of the left-hand side. Firstly, we need the satellite data, right? That is looking a little bit like that. However, as you remember, the ground truth is very important in our supervised setting that we will use tomorrow. Which means nothing else than we know for all of the pixels in the kind of picture that we have from the satellite data, it is a building, it is a light train, it is soil, and so on. Right? 9 classes. Still not really a challenging data set, to be honest. However, much more sophisticated than our IRIS flower data set we look at. right? And then it, of course, matters now what model and algorithm you pick. What do you think would we achieve with a perceptron learning algorithm in that case? Any idea? Would that work? No chance, right? So it would be, firstly, not really linearly separable. Secondly, it's a multi-class problem, and so forth. So hence, we switch to a new model tomorrow, which would be the support vector machine, which actually establishes also a line, but it finds the optimal line. But the extension is to multi-class systems, and then with kernel methods, you go into an interesting feature space, as we call it, to actually create very sophisticated nonlinear boundaries. This is not all obvious to you, that we will see how that materialized through the lecture 4, 5, and 6 tomorrow. But what we also will use is an interesting fact that relates a little bit how the data is actually prepared. So you see that a little bit here on the top part. So we don't work just on the satellite data and on the ground truths. We prepare the data. And some of the people here in the audience already asked me in between breaks what you do with data. This is an example of feature engineering, right? Where you do some mathematical morphology of some attribute filters with the same picture, so to speak, but you're changing it. And this largely means when you want to classify a pixel, one pixel in an image, what would you be thinking is helpful in this? Short question on that. If you think other pixels in the image.
Intensity.
Sorry?
Intensity values.
Intensity values, yeah. That is, for instance, something interesting when you have different gray levels in an image, yes. But when you think about the neighborhood relationship, right?
The contrast is...
Yes, contrast is also interesting, and basically the neighborhood. Right? If you now have land cover, think about this. You're landing here in the river. There's a highly likelihood that the pixel nearby is rather water than building, right? When you have already a water pixel. So, and there are specified mechanisms in feature engineering that do and put in this neighborhood relationship. So we don't really anymore adjust basically pixel by pixel classification. We really help with search tools like the one we will use and that you use today, tomorrow. Actually, of using the self-dual attribute profile, which one of the PhD students from me were creating in his PhD. 3 years, basically, and then we will take up this in the deep learning tutorial that follows 1 week later, and we'll see how deep learning achieves some of these things extremely automatically, while this is really a hand-engineered, manually prepared data set. We will see then in the deep learning tutorial how this can actually also automate it. However, the idea would be then we give this also to the classifier together with the spectral channels like RGB and infrared. We also have this prepared data that we will use tomorrow, and we also hear a little bit more about tomorrow. And so that is the idea of creating something more in machine learning. And in many cases, that's the point I wanted to make with this from the practical perspective, much time goes into this, right? Actually running the model, doing the machine learning aspect. This is less time. You would say maybe on the ratio of 30% is the modeling, doing machine learning in terms of artificial neural networks, SVMs. More time you spend on this. Feature engineering, feature preparation, feature selection. You think about your data, how you can better the classifier. There are different mechanisms. One, who knows, principal component analysis, maybe some of you have heard from this. Exactly. One example, right? Before you basically use data, you would put it to the principal components, and then you basically have a better content, so to speak, of your information, and you remove those which have, let's say, very less content, and you have much better modeling on these principal components. So this is just an example what you can use, and then you are not really restricted to just use one of it. Right? We will see that tomorrow. We use, for instance, kernel PCA, then this ESTA, our own feature engineering on top of it, then training the SVM model. However, the basic concept that you learned this morning basically was training set, using for training, having the ground truth, the testing with the test set, the model and train and evaluation training test will remain also in support vector machines. Right? The same as perceptron. That is basically the same idea as we have done before. And then you can play around with this and basically have different parameters when you basically have the resolutions here. Of course, this is also then parameters. The feature engineering aspect of it really means you have to think about now about different areas of shapes and also kind of add to the parameters. It's something where you not say, this is my feature engineered thing of the satellites, now I give this with the machine learning and then I'm done. Hence the CRISP process. You go back and see, okay, this was not good accuracy, maybe I use another part of the feature engineering process. If you think now about the neighborhood pixel, it depends a bit maybe of thinking how much of the neighborhood pixel you really take into account, right? So to which extent it is useful and not. So it's another parameter to think about, which is not actually in your model, but it's a parameter for your feature engineering process. And this is something where, of course, the data is also there. All of our data sets are actually in B2Share, if you want, open data. Of course, it's already downloaded also in our cluster. And now for this, you basically should look a little bit inside the cluster and see we have another interesting directory for you tomorrow that we see here. And this is a classification one. Right, whether it's Indian, Iris, Rome, and the scripts again we're going to use tomorrow. The Iris you already know from the morning, and now we're talking about Rome. So Rome is a very nice one, which actually works also well in R and MATLAB and others, and also very quick because it's a relatively small data set. Right, now when we think about going more sophisticated tomorrow, that is another data set we're going to use, which is 52 classes. Right now we're getting much more complex, right? We don't have any more 9 land cover masses. And this one is particularly interesting data set because it has mixed pixels. So what is that going to mean? Now the previous one was very clear, saying we have water, we have a tram, we have, different aspects of buildings. But here it's not so clear. So people have been using this partly in the field and doing labels and were unsure. And would say, and creating this mixed pixels and say one area has maybe soybeans, no-till drill, another one soybeans, no-till, so you see the soybeans alone are everywhere and mixing with the classifier here. So it's a challenging data set from this perspective that the labels are there, but it reflects a little bit to the data quality aspect we discussed before, that the label is now a bit, uncertain. Hence, our modeling would be distorted by it. With this information, we cannot go towards 100% in a sense, right? Because we are here and there unsure. Another challenging aspect is that we have here, for instance, 14 samples, 130 samples. Others, we have 1,000, that is good. We have 10 samples for a pond. So you see underrepresented imbalanced class problem here. So another challenging part of this data set, that's why it's kind of a benchmark in the community really to use that. And if you use here, MATLAB here and there, it takes quite a long time, the 0-1, to get going, with cross-validation, model selection, things we will explain tomorrow. But that's why this is very interesting. Yet it's labeled, which is nice, we have a ground reference. And again, of course, we don't have, let's say, just one image that many people think about remote sensing. It is actually looking into the Earth with the spectral challenge. The spectral channels, and then have basically more a cube representation of your data, which makes up the dimensions. Right, you have up to 200 dimensions just of different spectrums of light, which brings us another problem we will look in tomorrow. And this is a case of noise. Again, we discussed it a little bit today, but noise in the data could also harm your classifier. What I mean by this is, for instance, some of the spectral channels are overlapping, so we have kind of the data twice, bringing in noisy data, so there are different aspects with it where we have to be careful. Again, when we do PCA and feature engineering, of course that helps the classifier, but if we just use the raw data that is coming now from the satellite and compare this with our ground truths, we get a kind of 40% tomorrow. And then basically when we have the feature engineering versions and so on, which are smaller in size, but much more high quality data, feature engineered, we get up to 70% and more by support vector machines. And interestingly enough, when we then already jump, maybe as a sneak preview for some of you that also have the deep learning aspect, we use the same data set next week for deep learning, and we'll see that even this automated feature learning will increase again the accuracy compared to the manual feature engineering process. But this is, let's say, then really something for next week. How we use it is basically, again, tomorrow with different kinds of prepared data. So the Indian set, as you know, is already there. And take away the message, this is really the processed one, really much prepared. So lots of manual time-consuming time goes in there to get the high accuracy that we will see tomorrow. It's also a kind of message again to you. When you are in machine learning, don't think always throw the data directly to a model or to your system to create a classifier or clustering. Firstly, think about how you can better represent the data. Here was the idea, as I told you, basically before, with the neighboring pixels, you can basically create a tree of your different neighborings, and you can cut the tree at several points of saying how much of your neighborhood should be basically going in my current pixel classification. So this is something what we do, preparation of this data set. Lots of time goes into that. And then you start with a real classification, which is perhaps something like 70% of your time and 30% of your time, and in some cases even more, right? We just talked in the break about the biodomain, genetics, genomics, huge number of features, right? Where we have lots of problem of really grasping the situations in machine learning, mostly because we have not enough labeled samples, right? We have not, otherwise we would have perhaps cures of many of the diseases already if we would know perfect everything and have the possibilities of really doing this machine learning. Right, but in a way, what we will do tomorrow as a side effect we'll learn using parallel computing are these two ways. So we will use the big data as it is, right? Because it's in the moment also lots of the media. Just use the big data you get information from. But we will see that this kind of first channel of using it with cross-validation and then training still doesn't give us satisfactory results. So we have to go through a long pipeline of manual work, kernel PCA, the extended SDUB, and then some other feature extraction mechanisms to get good accuracy. And when you work in the field, you will see much of this will basically determine your work time, right? Deep learning is a bit of change in that, right? So that lots of these features are automatically created, but also there you spend then more time, or the time is then basically a little bit shifted to the creation of the deep learning networks. Because it's not like a typical feed-forward neural network, just a couple of neurons, you have to switch different layers and look at this. So also the Indian Pine dataset is available on B2Share. If you want to use it also after this tutorial, of course it's there. And as you see here, it's in the raw and the training and test. It follows all the SVM format that we discussed, so the class representation, and basically this kind of things, what we will look now a little bit inside. And then this is a small video, we really call it a day, I think. I see tired eyes here and there. So in the directory here, it's already prepared for you, and we will use it tomorrow. Other two data sets I just discussed. So we have the Indian processed training and test set, which are really small, right, in terms of kind of their kind of content and of their part, but it's very much, prepared features. So this is where all the manual feature engineering process goes in. Hence, a classifier is much more easier to create a model from that, very smaller runtimes. So if you use a raw version, that is really more or less how the satellite sees yours. And when you want to throw SVMs on this, which is interesting, which we will see tomorrow, you see that your accuracy cannot keep pace with manual feature engineering. Still take away the message, essentially no time, and you classify. And here, this guy, this PhD student of mine, Gabriel, was really 3 years working more or less in his PhD on preparing this data in such a way. And there are many tricks in the literature, right? You can always sample out a few which are not enough samples, and there are lots of possibilities of having, for instance, just 30 of the 52 features done, which is very easy because you sample just 30 out that are not making sense. But of course, this is then not, let's say, fair comparison anymore to this model. Here we use almost all, I think 6, we have really removed, and then we add this of the deep learning next time. How it looks like is no surprise. Perhaps shortly we do a tail, maybe or something like this. Again, it's the libSVM format. what you now see here is lots of more features, right? Here in the sense that 28 and so on. In the other eras, we just had a couple of ones. And here you see the different classes, class number 48, 48, 23, and so forth. So this is interesting for us, and we will explore that a little bit more in detail tomorrow. Right, and with this, if you have looked a little bit on the data, which I assume now you understand and have a good feeling for it, we will continue tomorrow. Before we close today, I think let's have a short video that you really understand what remote sensing is. It's a little bit my field of study, so I encourage every one of you to also engage in the subject and why you will basically hear now.
Remote sensing is the science and art of determining what's there without being there. Okay? So one of the things we do is to look at reflected sunlight. And there can be reflected sunlight giving us colors that we can't see. The visible part of the wavelength region that we see is very small compared to the total amount of reflected sunlight that comes off the Earth's surface. So if you look at all of that, you start seeing an enrichment of information about what it is you're looking at. Now, if you add to that the thermal infrared, which isn't reflected sunlight, but is heat emitted by the object that you're looking at, then you really do have a wide variety of wavelengths of light, electromagnetic radiation to look at. And then you can start answering the question, what is it made of? Because spectroscopic techniques have been used in the laboratories for decades before the first remote sensing satellite went up. And they would use it to determine the chemical composition of things that had an unknown composition. Now, this kind of information, this looking at the Earth in many wavelengths of light, which is multispectral, it means many wavelengths. Hyperspectral means very many wavelengths, or as the French say, beaucoup wavelengths. That is what you need in order to determine the chemical composition of what's there. And finding out the chemical composition is far more useful information many times than knowing the shape and size of the object. For instance, if I had the spectrum of the paint on your truck, 1 pixel the size of your whole truck would let me identify that truck, because I would be able to look for the composition of that paint. It wouldn't matter that I couldn't tell the difference between the cab and the bed, or that it was from this angle or that angle, or that was longer than it was wide. I don't need any of that. All I need is that chemical composition of the paint, and if it is a unique paint, I've got it. Now, a lot of times it's not so unique. It might be a paint that Ford Motor Company uses. Another one might be a paint that Toyota uses, or maybe they only use it on their Land Rover. Okay? Whatever unique chemical characteristics there are out there to look at, that's what you can go after with multispectral remote sensing. Well, I like to tell my students,
All right, so all the videos are, of course, in the lecture bibliography, so you can also look them on YouTube if you're interested. We conclude the day, unless you have any burning questions now. Of course, I'm here. Please feel free to approach me also after the lecture now. But is there maybe some question for the remote sensing part before we leave the audience today? Going once, twice. Everybody is keen to get home. I can understand. We start tomorrow at 10. I'm looking forward tomorrow to review with you more complex models. I hope it was a good insight today. See you tomorrow. Have a good evening. Thank you.